Hello friend, myself R.D. Mahajan presenting my video on the topic linear differential equation with variable coefficient type 1 Cauchy's form. Let us see the problem. Solve x d2y by dx square plus dy by dx is equal to 1 by x. Here y is dependent variable, x is independent. Order of that differential equation is 2. The coefficient is here x, which is a variable coefficient, and that's why it is in this form, linear differential equation with variable coefficient. It is in Cauchy's form, but for that we have to make the power of this term as x square, then only we get that Cauchy's form. Therefore for that, multiplying by x throughout, we get x square d2y by dx square plus x into dy by dx is equals to x get cancelled, we get 1, and we call this equation 1. It is in Cauchy's form. And as it is in Cauchy's form, we use the substitution log x as z, new independent variable z. Transferring this to other side, it gives x is equal to e raised to z. Then using capital D for the operator d by dz, we get we have x dy by dx, value of x dy by dx is always capital D operated on y, and second x square d2y by dx square as d minus 1 into y. Therefore using this 2 in equation 1 becomes therefore that equation 1 becomes x square d2y by dx square, we replace by this d minus 1 into y plus x dy by dx. The value of x dy by dx is capital D operated on y, and that is equals to 1. 1 we can write down as e raised to 0 z, and therefore it becomes, simplifying it, we get d square minus d and plus d operated on y is equals to e raised to 0 z. We call this as equation 2, and this equation 2 is linear differential equation with constant coefficient. It is linear differential equation with constant coefficient. Type 1. And then to solve it, we have to have obtained CF and PI by applying the finding the solution of equation 2 by finding CF and PI. Here auxiliary equation is d square is equals to 0. It gives d equal to 0 and d equal to 0. Roots are real and repeated. Roots are real and repeated, and as roots are real and repeated, we apply that technique of writing CF. CF is given by, it is C1 plus C2Z as it is repeated into e raised to m1 z, the value of m1 is here 0, therefore e raised to 0 z. This is nothing but c1 plus c2 z, e raised to 0 is 1, and it is equation number 3. That is CF. Then particular integral is obtained by that inverse operator technique, 1 upon f of d. Here f of d is d square, which we have to operate on e raised to 0 z, d replaced by 0, we get 1 by 0 e raised to 0 z. 1 by 0 means infinity, the value becomes infinity. Case fail here. And as case fail, we write next step as, here it is x means z, into differentiating it with respect to d, we get 2d, and operate it on e raised to 0 z. It is z by 2. Again d replaced by a is here 0, therefore 1 by 0 once again, e raised to 0 z. Second time case fail. Again case fail. And therefore we go to the next step as z square by 2 and derivative of d with respect to d is 1 and into e raised to 0 z, and that value is z square by 2, e raised to 0 is 1, therefore equation number next 4th as the pi. We stop here as we get some non-zero term in the denominator, and then combine this CF and pi to get the complete solution. Complete solution is always for the dependent variable. Here dependent variable is y. CF we have c1 plus c2z plus pi, it is z square by 2. We call as next equation number 5th as the required solution. Required solution is in terms of y and z, y dependent and z independent, but the original equations are in terms of x and y. Therefore once again we have to convert this solution in terms of x and y. Therefore applying that substitution here,